Assalamu alaikum everyone. Welcome to another session in Melody. Let me just share the slides first. Welcome to another session in Melody. Today we are gonna start our first ever kind of a series on scaling deep learning. It's called MLScale. We will see how to train deep learning models on large scale experiments, and not small scale on single GPUs or single CPUs, but we will do them on multiple CPUs and multiple GPUs. I'm not sure if there is any noise around me, but there is just let me know, and I will try to actually just fix the problem. Can you see? Let me just go to YouTube to see the chat and everything. But yes, so today we're gonna see how to train your machine learning models at scale, on your deep learning models at scale. It's me again, Bوحسين. If you are a follower of DevMena, I think you might have seen me in previous talks, and ML in depth, and also ML descent, and all those kind of talks. And at those talks, we were kind of speaking in Moroccan Derija. But this talk or this series will be in English, hopefully. And we will try to actually just use English for everyone in the MENA region to actually understand. And hopefully everyone kind of can learn something from this kind of series. So the goals of this series, it's not kind of, I would not say it's theoretical, but it's more on the practical part of deep learning, especially using JAX, Flax, and the TF and PyGrain. We will see some theories, but not that much theories. We will learn here how to build or to train your models from scratch using JAX and Flax. It's not similar to the previous talks. We were kind of just trying to run experiments, and we did not care about running at scale or anything. But we will try to actually run experiments at scale and learn how to use the available resources that are somehow free, somewhat free, even though limited, but somewhat free, and will help you actually train your models from scratch without relying on high-level libraries. We will check what is parallel programming with JAX and data shredding, what is it and why do we need it. We also check different pre-training, training kind of parallelly on TPUs and GPUs, on multiple TPUs and multiple GPUs. And we will see also how to implement masked modeling, contrastive learning, and pre-training. But this time we'll not discuss um, the theories, but we will kind of more be focused more on how to implement them, and then we will also actually just look at um, the um, the library weights and biases, and also the platform, how to use it, and how to kind of track your experiments and see when they fail, so you can actually just accept the training of your experiments and everything. So the outline of this kind of talk, even though I switched the position of these two slides. But the outline will be just why do we need scaling, just kind of bit of just me talking. And then we will go through an introduction to JAX and just see what is the basic operation that we can do in it, just mathematical operation. And then how to calculate the gradients, and then what is JIT and VMAP and PMAP. And also we will run a small experiment on a small scale Flax and JAX. So let's just get started again from the very top of the presentation, and let's just check. So the first thing first, why do we need scaling? When you are used to training your own models, not just loading large models from Hugging Face or anything like that, but when you are trying to own kind of train your model from scratch on some data set that you have in your lab or in your laptop, you generally just you don't find yourself in a need where you need kind of large compute or just a large GPU or anything like that. For example, you only have a data set of cats and dogs, and you're just trying to train a model on that data set. And you don't find the need to actually learn any optimization or any shredding or anything like that that we talked about earlier. You just need to call model.fetch, and then that will kind of take care of everything for you. And then you can report your accuracy and like test accuracy and test like F1 score and everything. Just like to share it on a small paper, like small like applied paper. But like when you are running, for example, like you don't need actually also like you don't need a lot of compute. You only need one GPU. You can actually train on that. But when you are dealing with, I would say, like dinosaurs or dragons, like datasets that are very large and models that are very large, then you will have a problem. You will not be able to actually just like run the same script that you usually kind of I used to write, just like kind of model.fetch. And there is not like enough libraries out there that actually take care of the pre-training scripts and everything like that. There's like some like in Hugging Face, but they are not kind of optimized for parallel computing, and they might be lacking like some speed and stuff like that. And you might need to actually learn to actually implement those models from scratch. Not only models, but also like the training scripts. Like if you are using, if you are trying to train a large language model using mass modeling, you need to kind of write those scripts yourself. And the main thing, like you cannot fit all of this, like the big model and also like the dinosaur data sets, like in a small GPU. So what you need to do is actually um, create a script that allows you to first like, take the model and replicate it on different GPUs, and then take the data set of dinosaurs that you have, and then just like split it on small parts or small mini batches, and then like replicates the models to actually on for three GPUs and split the data from three, for example, parts, and then pass each of those like kind of each of these pass them to the model or to the GPU that you need, and it will kind of predict for you the label or like the prediction, the logics, and then you will gather all of them on the like on the end of like on your session or notebook. You will use to gather them, and then you can calculate the loss of the final loss of your one iteration of your model. But the problem, the main problem, as we said, like when you're trying to train a small model, you are kind of like just like limited to the single GPU, for example, and you are limited to the CPU, you are limited to kind of like just like calling model of it. And but when you are trying to kind of like do all of this stuff, like replicating the model, splitting the data, and generating the random like batches or mini batches for your own kind of for each GPU, and also like the prediction, you will find yourself kind of your code will need to deal with how to shred with the data, how to kind of like split it, as we said here, how to replicate the model, and is there any memory leaks? Is there like any data duplicates that, for example, when you are doing the like randomization of your batch, and then you are trying to kind of create a batch, sometimes if you don't have full control over the like the backend, you will find yourself actually just like dealing with duplicates in your batch. For example, the random kind of the random number, like the random number generator, will generate for you kind of like two of the same kind of numbers, and then you will kind of get the same data twice, which kind of like creates like kind of, I'd say, duplicates in your batch. And then sometimes there is like memory leaks again, left and right. And sometimes when you are when you're trying to train a model using the gradient backpropagation or any gradient method, sometimes you might have like the gradients kind of exploding, and then when the gradient explodes in one GPU, it will kind of start creating non values, and then that will create like a lot of mess for you, and it will kind of screw with your results, and it will not allow you to kind of like train that model. And in the literature, when they kind of start creating like large scale experiments, they find themselves like kind of creating new problems, and then they will need to create some new methods for them to actually like mitigate those errors and mitigate these problems. And in this series, we will try to actually just like learn how to create those methods. And I know, like sometimes if you will tell me like, yeah, okay, I don't have any GPU, why should I learn all of this? Why should I kind of like learn all of this if you don't have GPUs? But you don't need to worry. Like Kaggle and Cloud allows you to actually use multiple GPUs and also like 8 TPUs if you want to kind of train any model. gives you, for example, Kaggle gives you like around 20 hours a week of free TPU, like TPU v3, and they will give you 8 GPUs. You can run large scale, it's not large scale, but scale, like large enough experiments. And for example, if you want to train a model from scratch, like an LLM from scratch, like a GPT-2 from scratch or anything like that, it allows you to kind of like do that, and you can actually just like use them for free. And then whenever you are at the end of your quarter, you can just like wait until the next week, and then that will kind of like your quarter will actually double again or free up a bit, and they will give you more resources to actually train your models. So as I said, like the series goals is like learn parallel programming. Now you might have like some of these like notions that are kind of like put them at the end. You know how to pre-train your models and also like experiments monitoring by the end of the series, which kind of will take a year to finish. So like bear with me, and then I will share with you more resources if you don't want to wait for my talk each month. But like hopefully by the end of this series, you will be able to actually create any scripts or like at least like prompt ChatGPT or DeepSeek with the right kind of like questions for you to kind of like generate those. And now we will start just like kind of running a small like a live coding session like in JAX, just like the basics of JAX, not anything that is like kind of like advanced or anything like that. We will just like learn some basics of JAX and then we can actually go from there. But first, if you have any questions, feel free to ask. But if you don't, like, we can actually just like continue with the session. So let me call this session here. Like let me call this notebook. And then let's say one, and then I can actually share it with everyone. Uh, Let me just kind of not. No, I don't think we will use this one, but we will be using kind of the table actually. So first thing first, like, let's go with kind of like a Kaggle notebook, and then we can actually just like run this one first and see. Like this will be the final kind of, and then we will do this. We'll go to this. So first thing first, like we will learn some basics of JAX, I would say. And the first thing that we will kind of like do when we first see what is the what is the okay. So let's start with just like some simple kind of matrix multiplication and scalars and everything. So the first thing we will do is like import JAX and import. Let me just like make this bigger so everyone can see it. And JAX.numpy and just like let's do as GMP. So like JAX, you can say that JAX is just like kind of the NumPy like API on steroids, like NumPy API that can run on GPUs and also on GPUs, which allows you to actually do the matrix multiplication and also the vector multiplication, tensor multiplication on like large scale. You can actually do all of that like a large scale without any problem compared to NumPy that is mainly CPU based. They might have add some GPU support, but they were mainly kind of CPU based. So we start like with using JAX and the basics of JAX, and then in the next session we will learn how to actually pre-train or like do any other thing. So like with JAX NumPy, you can actually create an array. You can create a scalar, for example. Let's do just like an array. Array is equal to gnp.array. You have like the first array, and then you have the second one. And then you can actually do a simple matrix multiplication if you want to, like just like x or a, like but like let's do multiplication first d, and then like just like a multiplied by b, just like the two matrices here. And you can actually just like do that through the same API that you are used to. Right, too. Let's call them A and B just like for reference, like for easy reference. It's not defined. I forgot to run this out. And now you can just like get the result, which is also like an array because it did like the element-wise multiplication. These are two vectors, I would say, not A and B, but let's say A and B. And then here, let's do A and B. And then here, let's just like keep them like that. A multiplied by B, and then we can do, and again here, we can, let's do A is equal to GNP. It will give us like a matrix, and let's not do that. Let's do like the same square matrices. And then the same thing here, we can actually run it like on A multiplied by B, and then this will give you the results of the matrix multiplication or the multiplication of these two things. But I did not run this one. And now this will give you like the matrix multiplication between these two matrices, which is just like the square because they contain the same values. You can do the vector like A multiplied by A, and then that would give you the functions here. Got shapes that are not the same. We have 3 and this like 5. Okay. And then it will give you like the vector matrix multiplication. We can do also like the dot product. Let's do the GMP dot dot, and then it would give you us A and B, and that would give you the dot product between these two. And then we need to do the transpose right here, and that would give you the dot product between these two matrices here, like A and B. We can do also like the dot product between A, let's say A and 80, and it would give you the dot product between these two. And you can actually just like, let's try it with import numpy as numpy. Let's try the same operations here like that we did. N is equal empty dots array. Let's do it. Like let's do this, these two things. But of course, run this here. And you can do like IN multiplied by PN. And then let's do a comparison here. Let's do time. And then let's calculate this time that is required. It's just like 33 milliseconds. And then let's call this one and see this one, this one. Let's see how fast is it? Is it faster or not? NP time. It takes longer for some reason. Well, it takes longer just because it's not like that optimal. So how can we make it more optimal, I would say? So let's define a new function. Let's call it mathmil, or let's just like mathmil gmp dots, not even that, mathmil, and then id, and this then we return a multiplied by b. And then let's use this function here, a b. And then let's do this at JAX.tips. I will first do a warm-up and see how fast it got, and then we will do it again. And now it got even faster, maybe? Oh, it took more time. But let's like try to run it on larger matrix. Let's do A, that's not large either. A, let's do 4 multiplied by. So A now is like a matrix of, let's just like show it. It's a matrix of lot of kind of numbers. Shape is 40 by 40. It's like a 40 by 40 matrix, and let's just like do the same thing with B. But now let's just like do 5 or something like that. And then let's run this one, matrix multiplication. Now it contains the same number of parameters. Let's just like copy this one and then take it to the bottom. And then let's create like an and bn, and then let's take this one. Let's just like take G here, J, J, and then do the matrix multiplication. You can see that it's taken like 931 milliseconds, while this one only took us like 27.2 milliseconds. So what we did here is just like just-in-time compilation, or JET, where it compiles this function first, or this kind of like function. It take it, and then compile it first, and then when you run it on your own kind of like kind of code or your own matrices, it will not do the definition of all those parameters or anything like that, but it will reuse this function, or this pre-compiled function, or the JET function, to actually run the JITted function, not compiled, but JITted function, to actually run the operation. The only thing that you should be aware of is you should not have any, I would say like you should not have any kind of parameters that is kind of like defined or something like that inside this JIT function. You should try to keep it as much as you can a pure functional function, like that is not defining or having any prints inside of it or anything like that, then that will slow it down. It will not kind of function correctly. So like you will need to use functional programming if you are interested in it. And try to run it for the first time. Let's do this. Dot, dot, dot. It's 26 seconds. It does not take a lot of time, while the other one is taking too much time. The other thing that you will need to learn about here is the V mapping. And the V mapping is a bit kind of a different concept here. So let's say you have like this matrix, like the A matrix, and also like the B matrix, and you want to do the vector-wise multiplication, or the dot product multiplication divided, for example, by the Euclidean distance or anything like that. And you don't want to kind of like do any kind of like I'll say you don't need to calculate. You don't want to kind of calculate them using the normal way. You need to do them like vector-wise, for example, like just like for some optimization. So you can actually just like use the VMAP for wise multiplication. And then here you will just like define a function, f function, that does not mel, and then it does it using a and b, and then return a, or like a multiplied by b. And now using this function, let's just like jet it for now, JAX.jet. This function here. And then we will use it to do a VMAP, or just like a VMAP map null. And this equals VMAP.map null here. And now you will use it to actually do the map, and res is equal to VMAP A and B. And now you can do res, you can show it, and that contains the final results, kind of. No. So A and B, it should not be like that. It should be vectorized. It should not be like that. It should be vectorized. I'm not sure what's happening here. Let's ask ChatGPT. Should not be like that. And you can, did I do any mistake here? No, it's okay. So it's A and B, and then you will do the VMAP on like kind of like, I think it's, so it's second. Yes. Yeah, we had 4 and 20. which kind of like is the centralized 20. That's correct. I'm not sure what's happening. It was black. So like we have now the results. Let's again kind of calculate the timing that we had. This is useful. It might not like be useful for this small kind of example, but when you are doing kind of like a large matrix multiplication and you want to kind of like vectorize that operation on different kind of CPUs that you have or GPUs that you have, you can actually use this VMAP to actually kind of give each CPU or each thread in your CPU with a single kind of operation. And then when you are running it on, like when you want to get the results, it will gather all the results and give you the final result. You can actually just like use it. Another thing that you might be interested in, but if you have like the like other kind of PMAP, you can use PMAP if you have like multiple GPUs on the same map or in the same kind of like session or anything like that. But for now, we will keep it until the next session, not just like not to confuse you with all this technical stuff. Now we will do another thing, which is like, so for example, let's just kind of do a simple loss function. Let's do def is equal to what's this like fine p squared def is equal and the c true thread. This is like our loss function. Let's of course again jet it, like just the jets just like for now, and then calculate the c, and that will be the gradient. This is like the grad you would use. Tf.grad. It's similar to TensorFlow's one. It's called TensorFlow dot a grad no, gradient dot TensorFlow dot gradient. And there is also like the PyTorch one, which is just like backpropagate, I think, or just like I think it's backpropagate. It's the same thing. It will calculate the gradient of this loss function here, and then it will give you the grads if you kind of like grad MSE, and then visualize that. It will give you a gradient of MSE respect, just like it will give you a description of this function here. But let's just like calculate it. Let's just like let's do a simple kind of prediction and two. Let's just like threads. Okay, like this is the gradient of the MSE. For example, we have two arrays here, and we want to see like how far they are from each other, like using the Euclidean distance or mean square Euclidean distance, mean square error, which is kind of just the Euclidean distance between the two. And then we will do this, and there is a problem. I need to do real problems, real numbers, which need to be like 2.1, 3.2, and just like need to do some floating numbers. And that will give you the gradient of zero or the array of zero, which is exactly nothing because like we don't have any like it's the same point, so the gradient is always kind of zero. From between these 2 points is always zero, but for 6 it will kind of give you a minus zero, since you need to kind of if you multiply this by 2, it will give you 6. So like the gradient of this function from this part here, from this point here to this point, you need to kind of like bring it down or bring it back by 2 to kind of like get this result here, which is 3. And then like there is also like the but let's just like take an example for now. Let's just like do a simple kind of like XOR dataset problem. So let's do just like um, XOR data JAX, and then that then is equal to we need kind of like the then and also number of points, and then this will kind of like allow us to kind of then is equal to 2. And then let's just like do a random generator here. It's from JAX.random. and G key, and then using this key, we will kind of generate. Let me just bring it from another notebook real quick. Let's just like kind of ask ChatGPT to generate it for us. Let's ask Gemini. And then you can just like click on this one, and it will kind of create for you the code you need for that. And then you have the same thing, like you have a dimension, you have the number of data points for each kind of like data. And then you will create like a label data sets, and then it's just like ask it to plot data generated from XOR data gen. Then this will allow us to actually see if there's any like kind of if the data is correct or not. And then let's do this. And this is the XOR data. As you can see, like it's not linearly separable. You can see that the data points here are a bit like entangled, and you cannot create a line for you to actually do any like I would say like any lines to separate both of them. So now let's do a small experiment. Let's just like import Flax, and then we will create like we will use this library called Flax Linen. There is like two libraries, there's NNX and then there is Linen. For Linen, it's kind of like the original one, like the one that I actually use, and the other one, NNX, it's a bit like a library that is, I would say, like similar to like PyTorch. You can actually just like use it without any problem. So first, we will kind of create a model, like kind of a model. It's called an MLScale, and you will inherit, or you will kind of like inherit from a class model, and then we will need a function like init, and also like a function like let's just like do pass for now, and a function which is call. Let's also do a pass, and then another function. We can just like use these two, but like kind of another function, but let's just like use these two here. And then let's do self, and let's do just like self dot init. So it's cheaper, and then like let's do self dot head them is equal to head them, and that sort of key that we need. You can also like define the hyperparameters here, hidden them. We don't need any output them or anything like that. We just need the hidden them, and then you can do this. You can you need the output area, the output them, and you might need sometimes to have like a setup function that also like self. This setup function will allow you to actually, it will be called when the layer is created, and it allows you to actually just like create or prepare the dense like layers at the beginning before actually doing any like any training or anything like that, or before doing any call or anything like that. It will create these layers. So when you are doing a call, you will not be defining these functions again, but it will be just like using these predefined functions, and then just like that's it. It will not be there will not be any problem at all. But at least it's like for now, let's not do it. And then you will take the for example, let's do x is equal to n dot dense, and then it will kind of like take let's do the self dot hidden. And then this will kind of like create a function, like a simple neural network that takes in as a parameter here. Let's do is equal to just like 2, and then here is equal to 1. So this will be our output model, and that will kind of like predict the class of these data points here. And then we will also like import Flax, which is kind of like the library of optimizer from JAX. You can use it to kind of define any optimizer or anything like that. But let's first like do init like mul is equal to MLP like that we had here, and then dot init. And this will kind of, we are missing on G's. We have it as a key here, so we should be using it. Additional, but it's already counted. Okay, we can do it now. Let's remove the key from here for now. We're not using any dropouts or anything like that. So let's just like move it from here. We will need to do, let's define first, for example, first the mul. Let's remove it from here too. We have 20 more minutes, so let's do it first. Okay. We need to create like a simple first, like just like let's create input is equal to perhaps performance, for example, here, and then we will do more. Let's do the model call here first. The time. Now let's first like visualize this down here. This should only contain the kind of like the out or the middle, which is like ones of 1.2, which is like if you check the shape of it, will contain the same shape that we have defined for it, which is 1, 2. And this will be our input to the model, but it does not kind of yeah, it's the batch and then the number of inputs. We just like now do the init of the model, and that will take us like this, model of inits, the dummy, and then we have the params. But we have another problem. Super here, dot init. Let's just like not call it. And then let's do this. We'll just check the input. Flax model, and it's always good to kind of go back to yeah, it's the key and just exactly what we did. But we did not define the model actually correctly. I think we are missing something. And um, it's not super, it's like let's do MLP. Let me just go back to one code I have. And then next. Wait, since I could share with you some codes that I have. We don't need the init function here. Since we're not redefining everything, so we will just like we don't need it. We can just do this, and that will do. Okay, so now we can create it. This must be defined, and we don't have any compact here, so that's why it's creating that one. That's when you add like this compact, you will not need any a setup function or any other thing, and you can generate like you can actually initialize the model, and then you can have like you can use this model, and then you will do model.fly. You can actually use the params that we just defined to actually do the prediction. Now this model is not like it's not trained or anything like that, so we need to train it. First thing that we need, if we want to train it, we will need to define a loss function, which is just like just kind of the binary cross entropy. What let's do is just like using the mean squared error. There is no need for binary cross entropy in that complex. And then we need to define a train set. And then you can actually just like use the grad, the same thing that we had, like using the opt state, but let's just like use we can create like a training state. Let's create the training states for us first. Let's just like import from Flax, import train states. I think it's contained inside the train states. And it's in training. That's in training train states. So let's go there and then training dot train states import train states. And then using this train state, we will create our own model. It is equal train state. We will have like we will need to create an optimizer. So let's go back and we already imported like an optimizers here. Optax is already imported. So let's just like to explore it. Import optax optimizer is equal to optax of Adam. Let's just like use Adam for now. We will see some advanced ones, and here we will just like to and this will allow us to do that, and then we can use this one state.apply and to actually do the prediction. And this state here would contain the model and also like the parameters and also the optimizer, and this will kind of allow us to do a bit of parallelization of all the states of the optimizer and also the parameters, like automatically just like by calling duplicate in the future. So it's kind of like make life easier for us in the future. But now let's just like do it. Let's define again step, which takes the like the states and also like the x and y. Now instead of having the previous code that where you need to define the opt state and the parameters, you can also kind of contain all of that in a single state function or a single state object that contains both the parameters and also like the optimizer that kind of when you call the flight gradients or anything like that. So now we have this function here. We have the other one, which is the loss function. Now we need to do like an optimization loop. Trains for three for 10 iterations. And then let's do a for loop in let's say just like kind of then then just like train step on y, x and y. And we have the x and y is already like in the data set that we defined here, this data set. So we'll use it to do actually training, simple training. And then let's do like and plot the loss plot the here. That's we have the loss function. It contains the function that would kind of like print it for us. So let's run it. And now we have is not referable. And and now the model is training, and you can see like the loss is diminishing. Let's do it for 100 iteration. And the loss is kind of a bit kind of stagnated here. And then let's pass the model with the accuracy. is equal to Python and then here like this. So the accuracy of this model is 50%. And it's mainly because we will not like initialize the model with finally correct parameters. We only have one layer here to do the optimization. But generally, once you kind of create a deeper model here, you can actually get more better results, which we can do actually in future sessions. But for now, let's just like kind of go for a bit and see if we make it a bit deeper, will that solve the problem or not? It's still 50%. So like we will check more of this like in the future. And if you have any questions or anything like that, feel free to contact me or anything. Um, until then, I think this will be the end of the session. If you have any question, we will wait for 2 minutes or 3. If you have any questions, feel free to ask. If not, we will see you in the next one, inshallah. Hope to see you soon. I think there's no questions. But anyone is watching, if you have any question, like in the future, if you found this kind of code, just like feel free to ask me, reach me out, and I will try my best to actually respond. If I did not respond, don't take it personally. I'm a bit like very extremely busy, but like hopefully I will find time to actually just like respond. Just like send me an email. Don't use social media for sending me messages. I probably not respond to your social media, but if you send me an email, I will most likely there is a higher chance for me to come and respond to you. Thank you very much. I think we'll end this session here. Take care, everyone. Bye.